Okay, so we will resume yesterday's session. So I need to share my screen, of course. Okay, so just small comments and remarks. So yesterday we encountered two issues. The first one was that we were not able to use Scotch with a single process. And so I fixed the code. I fixed the code in a recent commit. Okay, so minor fixes from the tutorial, where we basically, if we call Scotch but require only a single partition, we just exit early by affecting 0 to the partition and just exiting. And there was also a not really graceful error when we were trying to do domain decomposition and call reconstruct dmesh with no overlap. Yeah. Yeah, the Zoom is open. Thank you. Okay. And so yesterday, at the end of the session, there were two questions. One was how to solve eigenvalue problem, and the other was how to construct a global solution. And so what I propose that we do now is to first solve the eigenvalue problem. I will go a little bit more into the details of how we do it, and also then how to reconstruct the global solution. And so in this case, the solutions will be the eigenvectors. Okay. So I will just remove the non-necessary script, let's say. Okay. And so we'll just run again the script from yesterday. And so the script from yesterday was just solving a simple Poisson problem, but in parallel. And also, last evening, I fixed my installation. And so now I should be able to go back to Hyper and it should work no problem. Okay. Okay. And so if we run this again, TMP tutorial, for example, for its decomposition. So don't forget that when running in parallel, by default, we don't have graphics. And so if you need graphics, you need to put WJ. It's decomposition. Okay. And so when we run this, we have the domain decomposition, and we have the solution of the Poisson equation in parallel. Okay. So when we want to solve eigenvalue problem, there are many problems. There are many different eigenvalue problems. Okay, and so, for example, so when we look, for example, for x equal lambda x, this kind of problem is usually easy to solve if we look for the largest lambda. But when we look for the smallest lambda, it's usually difficult. And so there are ways to overcome this numerical difficulty by instead using a so-called spectral transformation. And so one of such transformation is called shift and invert, or just invert in practice, where instead of solving this problem, we will look for the smallest, and we will just do something like x equal a minus. And then we do 1 over lambda x equal a minus 1x for the smallest lambda. Okay, and so because we need to apply this inverse, okay, so the action of the inverse of A on multiple vector, we will need to use a Krylov solver, and we will need to use a KSP. Okay. And so in practice, instead of using the operator at -1, so solving a linear system, we can use EPS solve. And so EPS solve stands for eigenvalue problem solver. Eigenvalue problem solver. Okay, and so this is linear. So what we say here to, so this is SLEP-C under the hood. And so what we say to SLEP-C basically is that we are looking for the eigenvalues closest to 0. We want to use a spectral transformation of type shift and invert. And we have some tolerance for the convergence of the eigenvalue problem solver. And so, for example, I will decrease slightly this one. Okay. Okay, and so at the end, I output the values in MATLAB. So I will forget about this part for now. Okay. And okay, so this should run. Or actually, let's just put them so that we are sure that we are solving the proper problem. Okay, so these are the smallest eigenvalue. If you want to look for more eigenvector, you can, for example, use EPS NEV and something like 10 eigenvalues or 10 eigenvectors. Okay. Here we have 10 eigenvectors, and of course you can have SLEP-C or PET-C compute a lot of statistics for you. So for example, you can look at the error with respect to the computation of the eigenvalues using the parameter EPS view relative error ASCII info detail. I think this is okay. I'm not sure. I think I got the option wrong, but that's okay. I will just up. Give me 1 sec. Ah, of course. No. Okay. ASCII. Just give me 1 sec. Tac. Tac. EPS error backward. So we compute the backward error made on the for the computation of the eigenvalues and the eigenvector. And so this is shown here. Okay, so the backward error is not the most easy to understand. So maybe we will just look at the relative error. So not backward, but error. Back. Okay, so here you see very large values. So you may be thinking, oh my God, I'm not solving the problem very accurately. But once again, it's an issue of TGV. So in practice, in A, you have to remember that we have terms which are of the order of 10 to the power of 10 to the power of 30. And so in practice, if you want to compute proper error, I would always advise you to use TGV equal -1. Okay, and so you can put that before the assembly of the variational formulation. Okay, and so now when you do this, we have much better errors with respect to the eigenvalues. Yes. What does it do basically? TGV. Okay. So for that, I think it's easiest if I show you the tutorial. Just give me 1 sec. Talk. Tab. Oh. Single page, c'est où? Si, C'est bon? Désolé, hein, je vois pas du tout mon écran. Ok. Tac, tac, tac. So the default value of TGV is 10 to the power of 30. And so that means that we impose directly boundary condition using penalization. So basically, we first assemble the bilinear form without any sort of directly boundary condition. And after that, we post-process the system. And so FreeFrame looks for all the boundary values. And whenever there is a directly boundary condition, it adds 10 to the power of 30 on the diagonal. And so it does the same for the right-hand side. And so that way, when we solve the linear system, we know that for the solution, we have the proper Dirichlet value for x jd. Okay, so D is the Dirichlet nodes. So this is exact penalization because we are using double precision arithmetic. And so in practice, we have very high order of magnitude with this 10 to the power of 30 compared to the finite element analysis. But you can see that when you compute matrix vector product or stuff like that, it can introduce artificial noise. That's why we had large values in the error just previously. And so I often advise people to use instead other values for TGV. And so when we use TGV equal -1, in practice, it means that we do non-symmetric elimination. So for nodes associated to Dirichlet unknowns, we put 1 on the diagonal and 0 on the row. So that means that the problem becomes non-symmetric, even if you are discretizing a symmetric bilinear form, but it's much more stable numerically. So whenever you do eigenvalue analysis or when you do iterative solver, when you do nonlinear solvers, it's most often recommended to switch to something else than the default TGV. And in fact, here the problem is symmetric, so we can use TGV equal -2. And so TGV equal -2 does symmetric elimination. So not only it puts 0 on the rows, it also puts 0 on the columns.
Yes, but your problem can become not symmetric.
With TGV equal -1, yes. With TGV equal -2, it remains symmetric.
Okay.
But it only works if you have homogeneous Dirichlet boundary conditions. So JD equals 0. Okay. So in practice here, I think, yes, we have homogeneous Dirichlet boundary condition. So we can use TGV equal -2 and it will work just as well. Tac. Yeah, we have roughly the same error. So TGV is, no, TGV, you have to put it before any bilinear form or linear form assembly. Yes, yes, exactly. So Neumann is natural boundary condition, so there is nothing to do in the linear system. In finite element, with finite element, the Neumann boundary condition are not. No, if you have a pure Neumann problem, so no on your varef, the value of TGV does not matter. So whether you put 2, -2, -1, it does not matter. Yes, yes. If you have a pure Neumann problem, it's usually indefinite, so you need to have the Lagrange multiplier and. For Lagrange multiplier. Okay, I can try, but we have so first we just need maybe we'll do it later on. So I just want to continue and go back to yesterday's evening question. So of course here this is a standard eigenvalue problem. If you want, you can also solve a generalized eigenvalue problem. So X equals lambda bx. And so in that case, you need to supply another matrix. And so here I will do it. I will do something very stupid. I will just solve a generalized eigenvalue problem, but with a B, which is the identity matrix. And so hopefully I should get the same result when I call the EPS solve. Okay, so to do that, I can just use a new mat, define a new mat. And so the mat will have exactly the same distribution as A. And so I can do something like A dot n. And so what this call will do is basically create a mat where the local number of rows and columns, because this is a square mat, where the local is the same as for A. Okay, and so in this mat, I will just put the identity matrix. So again, we can use the new MATLAB-like syntax, matrix AID égale identity of B.N, and then I can put the free-form matrix inside the PETC matrix using the notation B equal identity. Okay, and so now I will just duplicate my EPS solve, but now I not only need to supply my A matrix, so the left-hand side of the generalized eigenvalue problem, but I also need to supply the right-hand side of my generalized eigenvalue problem. And so I do this with A, comma, B. So you would maybe something like so it's not in the API for now, but we could add it. Yeah, okay. So of course, yeah, we could do something like a tag, for example, 1 to say that we have a constant diagonal matrix. I need to add it, but it's not current. So if we do this currently, I think we'll get something, some sort of error like impossible to assign a double to a mat. Let's check it out. We have okay. So a lot of errors, in fact, but it's definitely doable, but it's not currently in the PETC FreeFM plugin.
Just to check the machine.
Okay, just give me 1 sec. I will go back to a functioning version. This should, the size of the mesh. It's okay?
Yeah, I just got in my EPS service statement way
On how many processes? So if you do EPS monitor, do you have some sort of log? Actually, there is. Okay, so this is the first eigenvalue problem being solved. No, sorry, this is the second. There is too much text. Okay. I think I know why it's taking long for you. Did you have the call to set A as params something or not? Okay, I will check if it's the source of the slow.
PC type A, mais moi j'ai gamme.
GMG? Et t'as TGV ou pas? Ok, et si tu mets -2? Et EPS monitor, ça te retourne des trucs ou? Okay, so this is the second solve. So okay, 0.01 and 0.002, and the first solve 0.01 and 0.002. Okay, so solving a generalized eigenvalue problem with a right-hand side, which is the identity matrix, yield the same eigenvalue as solving a standard eigenvalue problem. Yes.
Here you just export the eigenvalue on the output of your if you want to get this.
Yes.
You will maybe talk about that
right now.
and get also the eigenvector.
Yes. So now, okay. So if indeed, So for now, we have just done everything on the screen. So of course, you can also output this on a file. So for example, you can do something like ASCII my values.m. Okay, I will remove this call and I will just do one. Okay, so EPS solve, you can output this in a file. Okay, so now if I look at values, you have this in a file, but of course you may be interested in having this directly in the script to do some computation in the script directly, depending on the values that you get. Okay, so the API resembles what you have if you use RPAC. So RPAC is the old way of solving eigenvalue problem. And so the API is something like, it's really similar. You do something like eigenvalue, and then you put two matrices, so matrix A and matrix B. Okay, and so then you can also add additional parameter, and this is exactly the same here. So before this call, you can define, for example, real int EV of size, let's say I compute 10 eigenvalues, and then I can put as an additional parameter, so I always get the API wrong, but that's okay. I think it's something like eigenvalue equal EV. Okay, and so then if I do if MPI rank equals 0, I want to output the values on the terminal. Okay, so I got the API wrong. What is the proper? Okay, so you see all the values. Okay, it's simply values, not eigenvalues. Tac, eigen. Okay, and so now you see the values being printed preframe style, let's say. Ça mouline toujours? T'as mis EPS View ou pas? EPS Monitor?
Ouais.
Et il se passe quelque chose?
Non, il se passe. Non, j'ai changé P2 en P1.
T'es sur un Windows?
Non.
Uh,
The script just check the options and the set A.
So now I didn't use any set A.
Okay.
So actually you can try to remove it.
Yes. So now you are not telling it whether it's.
Yes, and so the default, no, so when the default solver, when you do shift and invert, is an LU factorization. And so the problem is small enough so that an LU solver is good enough.
Okay. Yeah.
Okay. Okay, so this is, yes.
Where do you find those parameters?
Excellent question. So, so this parameter, whenever you are looking for parameters with respect to the eigenvalues or the eigen problem solver, you can go to no, not here. You can go on SLEPCU's website. I will show you just one moment. So you can go on SLEPC's website, and so on SLEPC website there is a documentation. And there is, in fact, a really in-depth tutorial. I think there is even screencast. Yeah. So the main developer of SLEPC, José Roman, has done a really intensive screencast of
In this video, we are talking about
of how to install and how to use SLEPC. So of course you can just keep all things respected with respect to the installation. And I think you can go directly to standard eigenvalue problem. And whatever is showing in those screencasts can be applied readily in a FreeFrame script because the interface is a one-to-one correspondence. So, il y a une question? Non, il n'y a pas de souci. OK.
Just a remark or a question. In Atlas, when you solve a generalized eigenvalue problem, the eigenvectors are not normalized the same as the classical eigenvalue
Yes.
problem. Is it the same here? Or?
So you can specify how the eigenvectors are computed, how they are what it's called in CFC purified. So it's kind of advanced technique that I don't claim to master. So but it's possible to switch how the eigenvectors are computed after the convergence. Yes. Yeah, that's correct. That's correct. Okay. So this is the eigenvalue. Eigenvalue is easy because it's just a scalar. And so now we will want to, for example, process the eigenvectors. And so for processing the eigenvectors, we will need to first supply a vector to EPS solve, in which we will be able to store the eigenvector. And then we will go back to the answer from yesterday evening, where the question was how to build the global solution on the initial global mesh. So basically how to go from the distributed eigenvector to the global eigenvector. So I'm not saying this is something that you should always do, but sometimes it can be convenient to go back to a global solution just for the sake of checking that you are not doing something too bad or whatever. Okay, so just I'm just checking one thing. Okay. So just first, I want to see one thing, and I want okay. Just give me one sec. Okay. So just before we do that, there's one. Okay. So before we do that, I will show you one parameter when we use build a mesh. Okay, which can be used to perform automatic mesh refinements, uniform mesh refinement. Okay, and so this can be done if you want to generate large mesh starting from an initial coarse mesh, let's say. So actually, I'm not sure it works with a user-defined partitioning, but we will just try. And so the parameter is refinement factor. Okay, and so then you can do something like get RGV refinement factor, and let's say by default we don't want to do any sort of refinement factor. We don't want to do any sort of uniform mesh refinement. Okay, and so when I launch this, okay, when I launch this, it's not handled because I'm using the user partitioning. So let's assume that I don't want to use the user partitioning. Okay, so here, this generates initially a mesh which looks like this. Then we have a partition like this, and we have a solution. The solution, I'm not computing the solution anymore, I think. Yeah. Okay, and so I will put back hyper. Okay. Okay, so this is the solution on this mesh. And so using the mesh refinement, uniform mesh refinement, we can actually generate much larger problems. So if you do something like refinement factor 3, for example, of course, it will take much more time, or maybe not too much more. And you can see that the mesh is much finer, okay? So this can be useful when you don't want to deal with an initial fine mesh, because loading a centralized fine mesh can be quite consuming in terms of memory. And so instead, you can start with a rather rough mesh and then perform uniform mesh refinement. Okay, so this was one thing. And so now let's look at the eigenvectors. Okay, so for the eigenvectors, it's just as before, we need to add a new parameter, okay? And so whenever you have a function in FreeFrame which has a named parameter, but you are not sure of the API, you can just input noise. So for example, foobar equal something. Okay, and so here the something will be the eigenvectors. The eigenvectors. So what we know is that the eigenvectors will be an array of finite element function. And so my finite element space is called VH. And so an array of finite element function is called VH, can be parameterized as VH bracket int. And so this is eigenvectors. And so it will be also of size 10. Okay. And so here, of course, foobar does not exist. And so I will get an error from FreeFrame, and it will tell me the list of parameters, of named parameters that we can use, so that we can go back to the proper parameter. Okay, so again we see the nice list of parameters, and so I guess it will be something like vectors. Okay, so I replace foobar by only vectors. Okay, so I will decrease the refinement factor. I will increase the number of subdomain. Okay, so now there is no more, the script runs, and so I will just plot the eigenvectors. And so to plot the eigenvectors, I will just do the same as when we plotted the solution. And so to plot the solution, we use this, and so I will do exactly the same. And so I will loop for int I equals 0, I lower than the eigenvectors dot n plus plus I. And then I will plot th eigenvectors I, and so this will be my ith eigenvector. Okay, so let's check it out. There. Okay, so a little bit fast, but okay. So this was the solution of the linear system. So, this is the first eigenvector, second eigenvector, third eigenvector, so on and so forth. Everything computed in parallel. And so currently we can see that the solution and the eigenvectors are still kept in a distributed, okay? So now the follow-up question is how to go back to a centralized eigenvector if you want to do some post-processing outside of parallel FreeFrame, or if you want to do some analysis on something which is sequential and not parallel anymore, okay? So before that, we will just continue a little bit, and we will use VTK, okay? Because again, FFGlut is not the best tool for doing eye candy graphics. And so I will just show you how to use VTK really, really quickly. The important point is that whenever you do load PETSI, whenever you do load PETSI, you will automatically have access to save VTK if you want to save the output into VTK format. Okay, so you don't need to load IO VTK. IO VTK not needed if you already have the line above. Okay, so I will just comment it, but it should not be a problem if you still keep it. And so the API is save VTK. Save VTK, the name of the file. So eigenvalues eigenvalues.vtu, th, the name of the mesh, the name of the vectors that you want to save to file, And I think you also need to put order, which is something to tell whether the function is constant by constant by element or piecewise linear. And by default, we output constants by element. So we need to say that this is order 1 and not order 0, FF order. And so we want to make some sort of movie. And so, of course, we don't want to bother generating a movie. We want to let ParaView do it. And so to do that, we can use the flag append, which will basically concatenate the file one with another. And so we want to append after the first solve. And so append will be a Boolean value, either true or false. And we want to append only when we have already written the first file. So only when I is greater than 0. Okay, let's try. Okay, so error, no big deal. Qu'est-ce que c'est? Attends, je vais relancer en séquentiel parce que trop de messages d'erreur d'un coup. Ah, ok, d'accord. Int ff order. Ah oui, non, oui, ok, j'avais pas compris. Ok, int. Ok, so everything run. Tac, 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 tac. Everything is being output. And so now if we do ls, we see that we have a lot of eigenvalue files. And so we can simply open a main file. The main file will be eigenvalues.pvd. And it's running with 6 process, so it's eigenvalue underscore the number of process.pvd. Mince, j'ai tout fermé. C'était décomposé. Okay, so let's do open eigenvalue 6.pvd. Okay, so you need ParaView for this part of the tutorial. Okay, so I apply. And then I can look at the scalar one, which will be the eigenvector. And you can then go eigenvectors after eigenvectors. So everything is running nicely. Okay, so now the idea is to do exactly the same, but with a centralized output, because, yeah, just with a centralized output. So just as a comment, we can see here that we have, okay, maybe we cannot see, je ne suis pas un expert ParaView, le zoom. Tac, attends, ça va être encore mieux, je pense. Tac. Here we can see that we have a small overlap, okay? If we look at the surface with edges, we indeed can see that we have a layer of overlap in each direction, so in total 2 layers of overlap. But okay, so this is just to make sure that indeed we have a solution which is distributed on the mesh with ghost elements. Okay. So now the goal is to make exactly the same, but this time on a centralized mesh. So the same centralized mesh as in the beginning. Okay. So this requires a little bit of changes in the script, but that's no big deal. The first change is that we will need to keep in memory the initial global mesh, because you have to keep in mind that whenever we do the build mesh, so whenever we do the domain decomposition, we completely override the initial global mesh into distributed local meshes. Okay, so first I need to back up my global mesh backup th equal to th. Okay, so backup th will be the global mesh. And then we also when we do the domain decomposition, we want to let FreeFrame know to keep some correspondence between the original centralized mesh and the output local distributed mesh. So to do this, we have another macro that we can define, which is called the N2O macro, TH N2O. And then we have to use an array. And so, for example, I will name it N2O. Okay, so this is an array to keep the relationship between the input global centralized mesh and the output local distributed meshes. Okay, so even if you don't do any sort of parallel computing, the N2O parameter is actually really useful. For example, if you do multi-physics, and so I will just forget about this script for a couple of minutes, and I will go back to a sequential script that everyone can run on their machine to show you what's the N2O value and why the macro is called THN2O. Okay, so N2O demo.edp. Okay, so for now, I just shut down decomposition and EDP. Okay, so again, let's start with something simple. TH equal, let's say, square 40, 40, and then do FA space VH, TH, P1. On this FA space, we define a function, ufull, which is something like x plus 1. Okay. Now let's assume that we define a new mesh, which is the restriction, which is a restriction of the initial TH. Okay. So for example, you can think of a room where we want to extract only the bodies of every people in the room. Okay. So here I have a square, so it's not a room, and I don't want to do something complicated like shapes of people. So I will just assume that I want to split my mesh in two and solve one problem in part of the mesh and maybe another problem in the other part of the mesh. And so to do that, I again define a new mesh THB, and I can use the trunk operator. Okay. And so I will use a really simple Boolean expression. For example, I will keep only the left part of the domain. And so the left part of the domain is x lower than 0.5. Okay, so let's check this. TH, weight equal 1. CMM, CMM equal global mesh. I mean, no, full mesh. And then THB is restricted mesh. Okay. Okay, so this is the full mesh. And this is the restricted mesh. Okay, so no magic here. Now, let's assume that we define a new FA space on THB this time. And let's assume that we define a new function UB, and we want to just take the restriction of U on THB. Okay. So if you do it naively, let's say, you can, for example, do simply UB equal to U. Okay, so if we do this, CMM equal full U. Restricted U. C'est quoi? Ah, c'est U full. Sorry. Okay. So if we do this, full mesh, restricted mesh, full U, restricted U. So far, so good. There is one issue, though, if you do this. I mean, it's not an issue, but it's something which is quite inefficient. when you do the line 9, what FreeFM does internally is basically interpolates for all degrees of freedom in VHB the value of U full. Okay? But in practice, there is no need for such an interpolation because we know that one mesh is a restriction of the other. So basically, we just want to look at the arrays of the degrees of freedom of U full and just restrict and pick up the good degrees of freedom that are still in VHB. Okay, and so when you do line 9, FreeFM will interpolate the value. Yes, I mean, in the So in this case, THB is included inside TH. So the interpolation is the evaluation. But you can think of non-matching grid, in which case it needs to do some sort of interpolation. Okay, but in fact here interpolation is evaluation because basically what FreeFM need to do is just look for the nodes of THB and pick up the respected value, the corresponding value inside TH and take the value inside U full. Okay, but when you write line 9, FreeFM has no way of knowing that THB is included inside TH full. Okay, and so it still needs to perform some interpolation, which in fact is some evaluation, but FreeFM doesn't know that it can just pick up the value without doing any sort of interpolation. Okay. Yes, exactly. And so if you look at large 3D problem or large 2D problem with really bad elements, it can in fact result in UB, which is not equal to U full, even if you are exactly asking UB equals U full. Okay, and so to avoid such an interpolation, we can use a really useful parameter with the trunk function, which is the new to old parameter. Okay, so we need to add new to old, which will keep the relationship between the old mesh and the new mesh. Okay, so this is an array. You can put whatever you want. I like to call it N2O, but it's fine to call it whatever you want. And so basically what the N2O array will give you is the relationship between the elements inside THB with respect to the elements in TH. Exactly. It's a renumbering the restriction of the elements. Okay. So this is done at the mesh level, so the element level, and then we can couple this with another function to go to the FE space level. And so to go to the FE space level, we need to use the restrict function. Okay. And so we can do int my restriction equal. So the keyword is restrict. And so I always got the order wrong, but I think first it's the full FE space. So here it's VH, and then the restricted FE space, so VHB. And then the N2O parameter, which acts at the mesh level. Okay, so the restrict keyword is to go from the mesh level to the finite element space level. Yes.
What happens if TH has anything to do with TH?
It happens garbage, I think. Be careful. Yes. So if we do P0, P0. Yes.
In the case of the vectorial, of the line 2 and line, in that case, line also works.
Yep.
But the specifier is based on the node. Not the N2O is always the element.
Yes, elements.
This you can understand that it's vectorial or
Yes. Okay, and so now it's much more efficient because we won't do any interpolation. And so instead of looking at UB and U full as functions as finite element functions, we will look at them as vectors. And so to look them as vector, we just need to go back to the bracket notation. And of course, we need to pick up, or at least, or more precisely, to put in the proper place the values of U full into UB. And so this is done using the array my restriction. Okay. Okay, and so here I have a nice assertion failure, which means that I've got the order wrong, but it's always the case. It's first VH full and then VHB. No. Ah oui, pardon, excusez-moi. Yes, we don't go from the full to the local. We don't go from the local to the full. We go to the from the full to the local. So I've got the order wrong. Thank you. Okay, and so now, tac, 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 perfect. So be very careful in FreeFEM. Whenever you are dealing with finite element function, whenever you can, try to go to at the algebraic level, because at the algebraic level, all the operations are easy. It's just looking at an array of values and picking up the proper values and putting them someplace else. If you are at the analytical level, it's much, much more expensive because you have to call the finite element interpolator or evaluator.
What if the finite element space is P2 or P4? Is it the same?
Yeah, sure. Hop. No, yeah, élément P4. Tac. And okay, for Atsushi, let's try P4. Oops. P4, and then of course we need to do something like U full, oops, U full B, X, X minus 3. Tac, tac, c'est la même, c'est la même. Tac, tac, and of course here, UB, Y, and then UB equals U full my restriction. Tac. Comment? So P1 to P4 is in fact not possible. You need to call the interpolator. It's same as whenever you switch degrees. Whenever the FE space is not the same, you have to call the interpolator. Yes.
I don't find the restrict function in the previous documentation. How do you know that
yes, it was added. So it was added a long time ago, but it was added mostly for me, and so I was one of the only user, and so Frederic did not bother writing the documentation. So yeah, the documentation is this piece of code. Sorry.
Do you have some examples in the files?
Sure, sure. In fact, in the source file, repo FreeFEM source example HPDDM, restrict. Here, oops, no. So in the documentation, there is an example where we solve a problem in part of a domain. So we want to solve the Poisson equation just on the circle, and then we want to go from the circle to the full domain. And so there is an example in the distribution which does this. Okay. Sorry, there is no better documentation for now. Yes.
Yes, I have a question. If we have to use indirect element,
Uh-huh.
yeah, any problem with the number of doors?
No, it should work just the same, I think. So I'm not used to mixing restrict with nedelec finite element, but I think it should work. For example, okay, so it's not it it's not nedelec, but it's the I mean. Okay, so let's try RT2. C'est élément mixte. It should work. Maybe so if this does not work, so the restrict yeah, if it does not work, it means that there is a bug in the finite element itself. So the function restrict is just a map between the kernel of the finite elements. And so if there is a bug, it means that there is a bug in the finite element itself. Il y avait une question dans la Julien. Ah, sure.
Explain about the code-wise.
No, it's element-wise.
Not because of the atomic.
Yes. 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 Everything, yeah, N2, it's really important that it's element-based. Yes.
So since the receipt is the freedom, but I understand.
No, the degrees of freedom is restrict. N2O is really at the mesh and element level. Je suis perdu là. Okay. Okay, and I think maybe you've guessed it, but now the idea is basically to use all this machinery, but apply it to domain decomposition. So instead of doing N2O to go from one part of the domain to the full domain, it will be used to go from one subdomain to the complete domain and do the same for all subdomains. So we can just go back to the script via decomposition, I think. And so whenever you define this, it means that we want to let FreeFrame compute, let FreeFrame know that we want renumbering from the local to the global backed up mesh. Okay. So if we do a cout after this, we will be able to see that hopefully FreeFrame has properly filled up the array N2O. Okay. Okay. So for the moment, the N2O parameter is not compatible with the refinement factor parameter. So we'll just comment this out. Okay. And so indeed, the N2O parameter, the N2O array has been properly filled by the macro build dmesh or dmesh create or whatever his name. So now we will use this to construct the global eigenvectors. And so to do that, we will need to instantiate the FE space on the backed up TH. So backup DH, defined on backup TH of type. So I don't remember if I defined the func PK. Yes, there is a func PK here. But of course, so I will just put this before, tac. OK. Où ça? Huh?
Backup TH.
Ah, oui, thank you. Okay, and so after the domain decomposition, I can do exactly the same as on the previous script, and I can define an array which will be a restriction from the global backed up th to the distributed local th. So restriction from global to local equal restrict. Okay, so let's try to be slightly smarter than previously. The name of the script was c'est quoi? N2O demo. Okay, and the order is, oops, sorry. The order is N2O. So restrict, it's first the restricted FE space. So the restricted FE space in this case is just VH. And then the unrestricted FE space, in this case, it's backup VH using the N2O parameter. Okay. And so now we go down to the bottom, and so we just do VH, backup VH global EV. And then we do just as before, global EV, bracket, N2O, no, sorry, restriction global from global to local equal the local eigenvector. So eigenvectors. Okay, and so let's try just for good measure to plot this global EV weight equal 1, CMM equal 1. Sorry, CMM equal global eigenvector centralized on TH, on backup TH. Okay, so let's see. Spoiler, it won't work. Okay, so not because of this, of course, this is not expected. Identifier VH does not exist. What? Ah, of course. Back. VH is defined just here. Okay, so now, spoiler, it won't work. This is not the eigenvector. We, of course, only are doing the plotting on the first process, and we are doing the conversion from local to global on each subdomain. But now we need to sum up all the local pieces together. And so this can be done using an MPI collective routine, which is, for example, either all reduce or reduce. So now what we do is we basically sum up all the contributions together. And so again, this can be done using the MPI all reduce, for example, or we just do a reduce, in fact. Reduce. Okay, and so reduce, so global EV, and then global reduced EV. And so we reduce global EV. So all the MPI operations are done at the algebraic level. So it's global EV, bracket, global reduced EV, bracket. And so when you do an MPI reduction, you can either do a sum, a max, a minimum, Boolean or Boolean and so on and so forth. So in this case, we just want to sum the contribution. So we do an MPI sum. And we do the reduction and we centralize the result only on, let's say, processor 0. Okay. And so this is the global reduced EV. So even if the syntax, okay, let's see if the syntax is correct. The syntax is not correct. I guess I mixed up the order. Yes, you see that it's first the operation and then the rank. I mean, I used first the operation, then the rank, but it's first the rank and then the operation. So I need to permute the last two parameters. Okay, and so now, spoiler alert, it still won't work. Of course, it won't work because of the overlap. We can see here that on the overlap, we have complete garbage. Okay. So this is expected. And so in fact, this is one of the issues when you have ghost elements and overlap. And so we'll need to address this. And so there is two ways to address this. Okay. And so maybe the easiest way is to use the so-called partition of unity. And so the partition of unity can be accessed using the PETSI mat. And so in our case, the PETSI mat is called A. Okay. And so to avoid any sort of issue, we need to scale the eigenvectors by the partition of unity. And so this can be done using eigenvectors, again at the algebraic level, with a component-wise multiplication by the partition of unity. So to access the partition of unity associated to a distributed finite element space, you can use the .d parameter. And so now, hopefully, this will work.
The D here has the same ordering as finite element.
Yes, as the free frame local finite elements. Magic. And so here you can see that there is no domain decomposition anymore. It's the full mesh centralized on the first process. Okay, it's not ideal. In practice, in fact, I advise you not to do it, but it's just to show you how you can manipulate things and how to go from the local to the global and to do some reduction and so on and so forth. Okay. And so again, if you want to do some eye candy figure for your papers or for some communication, we advise you to use VTK. And so here the issue is that VTK will assume that you are outputting something which is distributed. And so you can use an additional parameter, TAC, which is the communicator parameter. And you can say that you only want to output on a local communicator. And so as we've seen yesterday, the local communicator is MPI self. Okay, and so this is meaningful only on the first process. So if MPI rank equals 0, 0, equals 0. Okay, and so this is centralized eigenvalues. Okay, let's give it a go. Tac. Okay. And so just as before, if we go back to a TMP tutorial, and if we look at centralized, we have all our nice eigenvalues. Okay, so again, we open the master file, centralized.pvd, and then ParaView is in charge of doing the heavy lifting for the movies and so on and so forth. Tac. So apply, I just, what? Ah, of course, hey, of course. Wrong mesh. Wrong mesh and wrong vector. So everything is wrong. This is backup TH. And this is not eigenvectors. This is a global reduced EV. Global reduced EV. Okay. So just for good measure, let's remove all centralized file. And then let's run this again. Okay. Tac, ls centralized. Okay, we still have the master file .pvd. We open it again. We remove this one. Tac. Boom. No domain decomposition. And hopefully the same eigenvector. Okay. So I think we killed the two birds with one stone, solving eigenvalues and going back to the global domain. Can you get only the restriction without? So yes. Yes. Okay. Good. Just you mean you want? Okay. So there is one. Okay. We can remove the ghost cell. There is two ways to do it. There is the easy way, let's say. So the easy way is to just look at the. Pourquoi on voit plus rien? Ah oui. Tac. The easy way is just to know a little bit about paraview and to play around with filters. Okay, so you'll have to help me out because I don't see filters. C'est où? Ah, mais tu veux pas que je triche avant? Okay, I will cheat a little bit first, just for graphical purposes. You can do a filter of alphabetical, no, sorry, alphabetical. So threshold. Where is threshold? On n'est pas encore au T1. Je suis pas sûr. Ah, mais c'est PQRST. On arrive au T, non? Okay. Threshold. Threshold. Tac. And so we do a threshold, not on the
Dans
scalar.
une demi-heure, le thé, il sera 5 heures.
Tac. We apply, and so the threshold, so this is a little bit under the hood stuff, but anyway, it's nice to know. By default, when we create the domain decomposition, the label of the ghost elements is -1, okay, and so if we remove like tac. Okay, so this is the first trick. If you want to do it directly inside FreeFem, you can do it, but yes. Yeah, it all depends on what you want to do. So just I think this is an interesting thing to look at. If you want to do truly non-overlapping domain so that you can output with just the skeleton, but no ghost element, one way to do it is to, for example, create a P0 partition of unity. Okay, so let's look at the P0 partition of unity. F a space P0 partition. So this is defined on the overlapping domain, but local to one process. And then you do P0 partition, my partition of unity. And so I think I talked a little bit about this yesterday, but you can have macro DDM create one for you using the create partition. Okay, so with the newer version, it's partition create, but no big deal. And so what it takes is first the th, then the function, and then the order of the partition of unity. So you can do this with P0, P1, P2, whatever you want. And so what we get here is, for example, this one, my Pun, CMM equal partition of unity on process 0. And then we do wait. Okay. What? Sorry, no way to plot. Of course, it's a finite element function. Up. So what is the partition of unity? In this case, it's a value, it's a vector which will be 1 everywhere except on the added layer of overlap. And so now basically what you can do is do something like mesh th no overlap equal trunk th apps mypen -1 inferior at some threshold new to old equal local restriction without overlap. Then you do restrict, and then you can again get just the local solution without overlap, save VTK, and so on and so forth. Okay?
The participant on the matrix in the vector. Get the submatrix from the.
Ah. So this is okay. So you cannot do subdomain by subdomain, but you can do it globally. Again, if you have if you have a big problem and you are just interested in a sub problem, there is a constructor which is something like mat B or restricted A equal A, and then there is an additional named parameter which is R, like a restriction matrix, in which you actually need to feed it a matrix of interpolation of restriction. So this is possible, but yeah, this is not the same philosophy as what we've done in the for loop. So we will need to do it someplace else. I mean, in another part of the script. So, but it's possible. Okay. Any questions? Any
I
comments?
have a question.
Yes.
Michel,
Yes.
what does the A dot D mean? Is it the diagonal, or is it something special for the?
It's just so it's just the use of notation. We have the habit of calling the partition of naming the variable used for the partition of unity by D, and so
Okay, so it's not diagonal of the matrix. It's something that's associated to the partitioning.
It's associated. I mean, it's definitely not the diagonal. It's really
Okay.
the partition of unity associated to the finite element space used to define the matrix. So it's a little bit of a mouthful, but it has in fact no relationship with the coefficient matrix A, but instead the finite element space, the distributed finite element space of A.
Okay, thank you.
You're welcome. Yeah, this is purely static. Do not try to do something like I mean, the partition of unity is always dot D. It's not I mean, you have access to other parameters like dot N, but in fact I think these are the only two, dot D for the partition of unity and dot N for the size, the local size of the matrix.
So what's the connection between A dot D and the P0 partition?
So in this case, there is no connection, but if you use the same finite element space, so for example, if you do this, this is a fun test. This is a very fun test. If you do this, hopefully, if I do my PUN minus equal A dot D, this should be really small. If it's not, then there is a bug. Assert my PUN dot L2 lower than 10 to the power of minus 10. Okay, I'm crossing my fingers because this is local. Oula, attends, j'ai cassé une partie de mon code. What part? Ah oui, ok. Tac. Ça coûte rien de le laisser. Quoique. Juste. Ouf. Attends. Ouf, mais en fait non, parce que là, je suis toujours dans FFBlut. Oh non, là, certes, passe pas. Alors attends. J'ai peut-être été un petit peu gourmand sur le. It should be equal. So maybe there is something wrong somewhere. Or maybe I'm just partition. Attends. Ah, je crois savoir pourquoi ça marche pas. Attends, déjà, que nous retourne ff-glut. On est bien à 0 là, hein. Je pense que je ne fais pas le bon calcul. Ah non, mais je suis bête. Je le mets avant la certe, du coup, forcément. Ah, qu'est-ce que c'est que ça? Ah, okay. Sorry. The partition of unity is only zeros and ones, whereas create partition may not be only zeros and ones. They may be 1/2. So yeah. So A dot D is always a Boolean function, a Boolean partition of unity.
Ah,
This one is always a Boolean partition of unity. This one may not be a Boolean partition of unity. It may have some zeros, 1/2, 1/3, and so on.
okay. Okay,
Uh,
thanks.
Non, justement. En fait, quand on fait le create math, je force AD à que des 0 et des 1. Ça simplifie un peu les opérations ailleurs. Et par contre, quand je fais le create partition, je post-processe pas la partition d'unité. Donc, des fois, il peut y avoir des valeurs non booléennes.
Merci.
You're welcome. Attends, les participants. Jules Bailly, I think so. I think it was you who asked the question yesterday about going from the local to the global mesh. I hope this answers your question. But if there is something which is not clear, please let me know, and maybe I can try to expand on the current code that we have.
I think it's okay for me. The main question was a bit with the magic manipulation of the partition of unity.
So is it slightly clearer or?
A bit, yes.
Okay.
But
Okay,
thanks.
you're welcome. Okay. Other questions or comments? Okay. So maybe I think, yeah, on the community forum, there was a question like 2 days ago about about defining a weird mesh and how to solve finite element, how to do finite element on this weird mesh. And so maybe what we can try is to go away from this really easy square and try some GMSH mesh. Unless there is some other topics that you want us to address. C'est OK pour les valeurs propres ou tu veux que je fasse un peu plus? OK. Ah. Yeah, sure. OK, so GMSH. GMSH. So I must warn you that I'm definitely not a GMSH expert, but in fact, I'm not sure I don't have it installed on my machine, so I will just put it here and install this locally, macOS ARM. Okay, macOS ARM, tac. Okay. And so I think there is some sort. I think they provide some. Yep. Okay. So they provide some mesh. I actually have no idea what the mesh is, so hopefully it's not too big or too difficult to mesh. But I will just download this file. So this is the GMSH Git repository. You can. I will put the link on the Zoom chat for those who want to follow along. Everyone in meeting. Tac. So I think I've downloaded the file, and so now I will just open up Gmesh. Open. Okay, so
I've opened Gmesh. File, open. Okay, I'm doing this on the other screen because it's impossible. Ah, yeah, I'm sorry. It's impossible for me to read. It's too small, so I'm doing it on my screen. Tac. Oula. Oula, oula. Je me suis peut-être lancé dans un truc un peu compliqué. Let's give it a go. So I think it's mesh 2D. I'm not sure even if it's 2D or 3D. So looks like 3D. Attends, je suis pas aveugle, hein.
On va voir. Ouais, il n'y a que la surface, donc on va faire le 3D.
Mais je sais même pas s'ils ont mis la 3D dedans. Si, magnifique. OK. And so now we just do. Okay, so this is where it gets tricky because there are tons of file formats. But let's try this. So I go inside TMP. I go inside tutorial. Where is the tutorial? Tutorial. And so let's do a GMSH file .mesh. Okay. And so let's try something fancy that's difficult to do with the GMSH plugin from within FreeFem. Within FreeFem, the GMSH plugin can only load version 2 files in, I think, only ASCII format, maybe binary, but I'm not sure. So let's try something that for sure does not work with GMSH load, and it's the binary version 4 format. And so TAC, and so I always forget if I need to tick those checkbox, but let's do it simply for now. TAC, okay. So now if we go back to the terminal, okay, we can start fresh, vi gmsh.edp. I think here I have, c'est combien T19? Non, c'est quoi? Il m'a pas mis l'extension, ce boulet. Okay, so false start, export. Ouais. .msh. OK. 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 Donc je supprime ça. Et juste, je regarde t19.msh. Yes, perfect. OK. So this is the part of the PETC plugin, which is the least tested. So last time I tried it live, I think it was 1 or 2 years ago, and this helped me discover a bug in PETC. And so hopefully this time around there is no breakage in PETC, but maybe this won't work right away. I apologize in advance, but okay, let's again load PETC. And as I mentioned yesterday morning during the presentation, whenever you deal with meshes in PETC, we deal with what we call DM, data management. And furthermore, when we deal with unstructured meshes, we deal with DMplex. Okay. And so in FreeFem, we can define a DM using the DM structure. And so I will just load my mesh, which is called t19.msh. Hop, msh. Okay, so let's go slowly but surely. ffmpeg run -1 gmsh.edp. Okay, so let's try something slightly more advanced. Let's do something like dm_view. Okay, nothing to show, but I'm not sure it's a bad sign. So of course there is not much to do with a DM. Okay, so we provided a utility routine to go from a DM mesh to a FreeFem mesh. Okay, and so this is done using the really simple syntax, at least in my opinion, with the equality operator. I think it's the equality operator. Okay. And so apparently we have again a breakage in PET-C Dmplex. Okay, so just give me one, maybe it's this. So just for good measure, I will check whether it's working in the distribution or not. Opt exemple HPDM, git dm, Dmplex PET-C. Ah, j'ai peut-être été méchant, il y a peut-être un paramètre qui manque. There may be a missing parameter to make things run smoothly. No, there is definitely okay, just one sec. Let's try a debug version. Sorry, I'm doing my debugging session. Just give me one sec. Tac. It's maybe I thought no. Okay, I guess I need to fix the preframe interface. So the Dmplex part of PET-C is the most is the part of PET-C which evolves the most, and the API is not 100% stable, and so on and so forth. And so when they change back and sometimes they change back and forth the API, and it causes some breakage. So apparently I need to fix something in the FreeFrame plugin, but I will try to take care of this rather sooner than later. It's il y a quelqu'un dans la pièce qui a un. Is someone in the room able to run? T'as la version 4.14? Tu peux faire juste FFmpeg run dmplex. C'est peut-être juste la version de développement de PET-C qui a changé. Et vu que moi j'ai une version de développement, juste FFmpeg dans le exemple HPDDM. Ouais, et tu fais FFmpeg run-np1 dmplex PET-C. Tout en majuscule DMP et après en minuscule Lex. Ouais, ça tourne. Hein? T'as un crash? Ok. So, non. Non, mais c'est pas grave. Faut que je répare le plugin. So I need to fix the plugin. There is some change in some places of the Mplex, which makes things incompatible with what we did previously, and so it's okay. But unfortunately, we cannot do GMSH. I mean, we can try to load it. We can try to load it. Tac. Export P80. .msh. But we'll have to resort to version 2 ASCII. Okay, maybe that's better. Okay, so let's forget about DM. Then do load gmsh tac equal gmsh load 3. I always forget about the API as well. No, okay, so I'm missing something. Export. Not working as well. Okay, so let's forget about gmsh for today. Hmm? Yeah, but I switched to 2. Even 2 is not working. Yeah. Hmm? Ah, that should, yeah. Yeah, let's try something. Repo, freeframe source. No, freeframe tutorial. Let's try this. Oops, oops. Read mesh, not okay. Application. No, no, no. Volume, gmsh, bit, non, resource, non. Application, non. Yes, thank you. Content, macOS, yes. Tag, no. So the command is -3. Then the geo, I have no idea where I put the geo. I think it's in download t19.geo and then t19.mesh. Download, yes. Okay. And then, c'est quoi le nom? Et donc, c'est donc gmsh.edp. And the mesh is messed up. So usually when you use dmplex, you can bypass such an issue, but since the plugin is messed up also, I will need to fix it first to be able to load the mesh. But this will be a good test to have in freeframe. So for now, let's stick to square for the end of the tutorial, or cube. I don't know if you have some specific questions or We can try to go back to the Lagrange multiplier.
I have a
Ah.
little question, really
Sure.
simple. It's when I build a square with one element in each side. So I have a square with two elements.
Mhm.
If I took P2 element, I am supposed to have 11, 11 nodes on it. That's
Mhm.
right.
Uh,
And
okay.
and if I plot a vector, uh, any vector on it, it'll have more than 11 points that appear to me. If you made a square of 1, 1,
Oh, yeah, sorry.
yes, on a
Ah, but
and on a P2, P2,
you mean P2, P2 or just P2?
yes, P2, P2,
Okay.
then you can have anything. We just have to give them a value to have a vector when we plot.
Yes, but the plotting, you have to be careful with the plotting because the plotting is only linear. And so what it does is basically refine the mesh and then interpolate from the P2 to a P1, P1.
Okay.
So what you say is that if I do that, P
For
dot
me, I am supposed to have a precise value on each node. If I'm in 1D, it's like only have one precise point by node. If I'm going P1, it'll have an interpolation supplementary, or if I go P0, he'll have just the value on all the node. I will try to be a little bit clear. If we plot this,
Mhm.
we are not supposed to have one precise value or one vector by node.
What do you mean by one precise value per node?
Because it's a P2 element,
Uh-huh.
we have it's not the precise value, but it's a approximate value precisely. So, but if we are plotting the mesh on this,
I mean,
look, if you do the plot again and
ah,
you add the mesh on it,
mhm.
okay, I expect on the top to have only three vector because I have one on the node at the top left, one on the middle, and one on the right, because it's a definition of a P2 element. On one,
Yeah, I think it only applies if you do P1. Because again, with P2, we just
with P1,
refine.
I'm supposed to have just two vector, one on the left and one on the right.
Yep.
But with P2, I'm supposed to have three, but FreeFrame show four.
Yeah,
So
but I mean, the visualization, you should not, I mean, yeah, high order visualization in FF Glut is not really ideal.
but
So,
but just my question is what I am saying. Saying uh, it's just an interpolation between two nodes of P2, or is this
no, two node of I mean, two P1 nodes are
yes?
interpolating all the, I mean, P1, there is an interpolation from from P2 to P1, sorry.
Okay.
So basically, I think we can get the same, you can do the same with something like merge th s equal trunks th1 split equal 2, and then do something like vhs stack, and then do vhs ab equal p q, and then do plot a b. Ah,
So basically for me it was on P0 we have the value on the barycent.
ouais, yes,
On P1 we have the value on the extremities,
yes.
and on P2 we have the value on the barycenter, the extremities, and the middle of
I'm not sure of, I mean, yeah, again, you don't use FFGlut for high order visualization.
okay.
Do not expect FFGlut to print what the real P2 nodes are, because FFGlut does some magic to go from P2 to P1, and so it's not, yeah, it's not that easy to figure things out.
Okay.
It's a little bit like ParaView. ParaView does not handle high order. And so if you plot, I mean, in FreeFrame, we don't output to higher order than 1. And so if you output a P2 field, for example, we just do some sampling and output everything as P1. So it's difficult to, I mean, it's not that easy to visualize high order fields.
Okay.
Yes. Uh-huh. Yeah. So you perform mesh adaptation basically. Okay. Yeah. So there are two ways to do mesh adaptation. Either through just before that, let's try Atsushi's solution. Oh. Yeah, sure. No. Okay, and so now it was GMSH. Ah, there is hope. Thank you. What is this mesh? No, but I mean, I'm not sure. Yeah. But is there tetrahedrons inside? Uh, Road MD. End of string will not be found. Ah, it looks like there are tetrade rounds. Okay, so maybe this was why it was. Maybe this is why it was failing previously with dmplex as well. But let's try it again. I think it will still fail, but there is a reload button, I think, in here. Geometry, reload script. Ready. Eh? Ah, je l'ai bougé. Ok. Open. Ok. Export. Okay, let's try again. Eh. Ah non, mais j'ai. No. Okay, so I need to fix something, or we need to fix something in Petsy. We'll have to see, but that's okay. Okay. Anyway, let's go back to. So I propose that we do mesh adaptation based on the eigenvalues, for example. So it was decomposition. Okay, so what's nice now is that we already have the centralized solution. And so there are two ways to do mesh adaptation. We can either use MMG or par-MMG. So MMG is sequential and par-MMG is parallel. And so for MMG, since it's sequential, it means that we need to have the centralized solution. And so here it's already available. And so, for example, what we can do is tac, if I'm on process 0, so load MMG. And so we can do something like mesh at th adapt equal MMG MMG2D th. Okay, so first we'll need to compute a metric. And so to compute a metric, you can use, for example, MSHmet. Okay. And so I'm not an expert of mesh adaptation, so I will just look at the examples. No, no. In fact, I'm not even sure. MSHmet only works in 3D. So let's do let's do eigen. And so it must be, so here we'll need to supply a P1 function, which is only defined on at the node level. Okay, so of course, this should probably fail. Okay. It- ah. So, tac tac, métrique. ISO. Ah, assert. Ah, oh. So here I'm adapting the local mesh, but I want to adapt the global mesh, so I need to adapt backup th. And the eigenvector is also the globally reduced vector. So global reduced. Ah, global reduced EV, and let's put a minimum size of for the triangles, H min equal a1 to the power of -2 for the moment. Ah. Okay. So we are at just I need to look at the values. Okay, so let's assume that we want to adapt with respect to the ISO value of the ISO value 0. So we can do ISO equal 0, LS equal to 1. I need to put less plots because it's impossible to look at the screen. Plot. Uh, So it takes a little bit of trial and error to figure out how MMG works. And so, yeah. Actually, I need to increase. Tac. Ah. Hmax. Nope. Okay, let's decrease again Hmin. Okay, I hopefully you get some idea on how to. Yeah, so in fact, so I think in 2D, I don't know how to do it in 2D. Yeah, but that's the thing. MSHmet only works in 3D, I think, but I'm not sure. Just let me have a look. No. Yeah, so let's try just plain adapt mesh. So MMG2D comes from the MMG software. And so it was really recently interfaced. Prior to this interface to MMG2D, the way to do mesh adaptation in 2D was through adapt mesh. Okay. So adapt mesh has been there for much longer. And so let's try adapt mesh. Tac. Maybe it will give better results. I think there are the same parameters like no NBVTX, NBV. No. NBVX. Is it any better? Not really. Oh, a little bit. But again, it's a matter of finding the proper parameter to get things running. Hmin or Hmax. Sorry, I'm not a mesh adaptation expert. Ah. C'est bizarre. Ah, non. Ah, slightly better. Is it okay? So of course, then you need to, then you need to, this is done only on process 0. And so of course, if you then want to do some adaptation loop, you need to broadcast the mesh generated on process 0 to all the other process. And so you can do this, for example, like that, mesh th adapt. And then do broadcast processor 0 th adapt. And so then you can do again, create mat, and so on and so forth on the adapted mesh. You're welcome. Questions or comments or? Yes.
Will you share slides?
Sure, sure. Tac, tac. Oop. So yeah, definitely can share all the EDP. I will just make sure that they are all running before. Okay, this one is running. This one may not be running. Oh, it is. Good. No, I think it was with 8 process. Yes. Okay, then there was also reconstruction. And to démo macro sec, c'est quoi ça? Ah, pas très intéressant. But yes. In fact, let me do it right now. No. Tar CZVF. If there are any tar CZVF tutorial.tar.gz Ah oui. C'est des tutoriels. Tous les EDP sauf macro sec. Tac. Ah oui, non, je suis bête. TMP tutoriel. Good. Jolive.et/tutorial.start.gz.
Mm.
So, it's a TARGZ. So just an arc, yeah, just
Range, okay.
no. It's exactly this URL that you are seeing.
Sorry, I have a question for you. Maybe it's a long question and out of the context. I read that there is possible to do optimization in parallel with Tau.
Yes.
And so I'm trying to export my sequential code. I do optimization with IPOpt. And I have maybe you have any advice or suggestion to extend this procedure. I read that there is some tau solve like interopod method or primal dual.
Yep.
But from the documentation, I see that there is only 2 examples, and I don't understand
Sure.
more.
So what's important when you think about nonlinear solver in PETSI and in FreeFM in general, and in with its interface in FreeFM, is that basically you need to provide callback functions, which either give you back a Jacobian or either give you back the action of, the computation of some residual. And so, let's go repo example. So if we go back, if you look, for example, at tau, minimal surface tau, you can see a couple of callback function. So for example, the cost function J, which will return a scalar, the derivative of the cost function, which returns an array. So yeah, an array of real. And I think there is also the Hessian, which computes an Hessian, so a matrix.
Yes.
And so, yeah, you basically, so if you have access to those operators, so if you are not interested in quasi-Newton or whatever, but if you have access to the Jacobian and to the Hessian, whatever we've done thus far extends to those kind of solver. You just you have to provide those callback functions. So basically the cost function, it's first order derivative and it's second order derivative.
Yes, I read also that if you have some constraints like equality or inequality constraints, you have to provide also to the Hessian the Lagrangian multipliers associated to that.
So it will depend
Like
on the type of constraint. So for example, if it's a constraint on the solution, and for example, you want X to be higher than some variables and
yes,
X lower than some variables, you can also, I think, supply those directly within the call to tau solve. So for example, here there is XL and XU, which is the lower bound for X and the upper bound for U.
yes, like in the IPOpt. And one last question. In the IPOpt, if you don't provide the Hessian, it will assemble it with BFGS, maybe LBFGS. There is the same option in tau solve.
I think there is. It's been a while since I used it, but let me see. There should be the same tau solve. Uh, oh, sorry. ls. Tau solve. Here we don't yeah, so for example, just give here, this is for example a quasi-Newton method. So
Mhm.
we don't provide the function for the Hessian. And down below it's a true Newton method, and so we provide the Hessian of the cost function. And so you have the option to either provide the Hessian or not provide the Hessian.
Okay.
So the mat H here, it's not used to, I don't think it's used for, tac. Just give me one sec. Yes. The function in this call to tau solve is not used to define the Hessian. It's just used to define the distribution of the data. But in practice, if you don't, you can call tau solve without supplying the Hessian of the function. So the support for tau, so tau has some ongoing development, but not the most inside PETSI, and the interface in FreeFM has not been. I mean, I've no real use case. So if you really want to tackle large problem, I'll be happy to guide you, and if you can contribute to the example with some more meaningful example, that would be really interesting. So this is something that needs more examples, need more testing. So if things are not working or if things are not clear enough, please let me know, and hopefully we can improve on what we currently have, but which is not 100% ideal, let's say. There is room for improvements.
Okay, thank you. Thank you very much.
Any other question? We can end a little bit early. I know some people have to catch train. I'm fried, so it's not that big of a deal. I'm surprised that Frédéric, I don't know what's going on in the other tutorial session, because yesterday they were done a lot earlier, sorry. Yes.
Question about division boundary condition.
Uh-huh.
In freehand, you use on.
Uh-huh.
ON,
Yes.
and also you use the healthiness of, so you somehow specify TGB,
Uh-huh.
and it's a huge number.
Uh-huh.
But can you just input or just specify the values, and not solving, not including the matrix? Is it possible? If you say that the matrix number is 100 by 100, but if you say that the Dirichlet is specified 20, then DOF must be 8. But it's not that way.
So basically just removing this set of rows and so it's expensive. In practice, it's expensive to change the sparsity pattern of a matrix, to modify a sparse matrix. And so we prefer to keep the matrix intact and change its numerical values. So we can do it. Actually, yesterday, Frédéric mentioned that there is the notation, something like IJ. Okay, so we could build the set of indices not associated to Dirichlet unknowns and extract from the matrix A just the appropriate one without directly boundary condition, but it's expensive. So
Sometimes it's confusing when I'm using Didrik element.
uh-huh.
Didrik.
Yeah, sure.
What does it mean?
Yes, yeah, that's true. But you'll have the same issue with just, I mean, you'll have the same issue with extracting part of the matrix. I mean, it's a matter of identifying the proper unknowns. And so then if you want to either just extract the unknowns which are not associated to directly, or just put something on the corresponding rows, I mean, yeah, the on syntax for an edge element, it's weird. I mean, for non-nodal elements, it's a little bit it can be confusing. I agree. Yes. Yes. Right. Uh-huh. Right. Yeah, no, it's no, that's okay. Maybe I can go on the community. Shoot. No, actually we somehow, so this is the post where the person wanted to do some fancy mesh, let's say. And so we succeeded in loading the mesh with the FreeFem GMSH load plugin, but not with DMPlex. So this is the part that I need to fix myself. So actually, I would be curious to see CD template tutorial VMT. This does not work, but I need to fix me bug DMPlex. Okay, and so this works, and I just want to see if we can quickly solve something like a Laplacian on this mesh. So ffmpl run -1. No boundary condition. So actually we can solve a problem with pure boundary condition, pure Neumann boundary condition, and impose the mean value with a Lagrange multiplier. So let's do varef vpb u v equal into in 3D ph dx u times d xv plus dyu times dy V plus dzu times dzv plus int 3d th v include macro ddm. Okay, and so we have to specify before that the dimension of the problem is 3. By default, it's 2, so we don't need to specify this, but here it's 3. Then we do mat a mat create or create mat a th p1. Okay, so just making sure everything's okay. No. What's wrong? Ah. What? I think there is something wrong with the mesh because I cannot even trunk it. Read mesh, c'est out labels, th. Ah. Ah. Okay, so this is the bug in FreeFem. This mesh is really nasty. Tutorial. So everything is sequential. Segmentation fault. Okay, no big deal. LLDB. Seg fault in adjacent link. Okay, I guess we are doing something that we shouldn't do. The adjacent. Oh. Dereferencing a null pointer is not very often a good idea. Yeah, so there is something definitely wrong with the mesh, but for next year, I guess. Oof, many null pointer. Ah, okay, it has no. Ah, okay, so that's weird. This is supposed to output. Ah, there is no physical surfaces as well, I guess. Ah, okay, so we don't have the surface mesh. And so yeah, in FreeFem, we cannot just load meshes with only t-thread runs. Non, mais je finis sur une segfault, là, c'est pas très encourageant. Ah, mais moi aussi, tu vois, on a une belle segfault, c'est magnifique.
Ah, toi, t'as une segfault.
Voilà.
Moi, j'ai eu des trucs qui marchaient pas, c'est tout, mais pas de segfault.
Non, mais c'est de la faute à GMSH, on va dire.
Ah, oui, mais j'ai un message, c'est par des Belges.
Ouais. Non, mais il y a plus de questions, là. On est dans les prolongations.
Bien, bien. Je vais poser ça, puis je reviendrai pour prendre.
Oui, bah, je pense que là, on est bon, hein.
Oui, oui, il est moins de quart. Bon.
À tout de suite.
Et quoi qu'il arrive, je vous dis merci d'être venu et peut-être à l'an prochain, on verra si.
On verra.
On verra si je suis.
Okay, so I will now stop the recording. And I think I will also stop the session. And so in case you didn't hear Frédéric in the room, we thank you all who are on Zoom to join for joining us. And hopefully we'll see you next year or on the community forum before that. So thank you.
Thanks for the tutorial.
You're
It was
welcome.
really good.